Okay. So last Saturday, we started discussing about generative adversarial networks, and we got the theory part, and we discussed about what we can do and do using generative adversarial networks, or we call GANs. And after that, we discuss about the process or the functionality of generative adversarial networks, and it was a very interesting thing, right? So and I discussed and I explained you what happens basically inside the generative adversarial network, right? So the main task or the main purpose of using a generative adversarial network is to generate or create what you call imitated data, or we can say artificial data, or we can say fake data, right? Fake data. Uh, so that's the purpose of actually, I mean, using generative adversarial networks, right? So this fake data generation. So for examples, we can say like fake faces, right? So uh, we can say like new music tracks, right? And new fashions, right? New styles, right? So it can be like batiks, right? So new batik styles, right? New clothes, right? Styles and new car designs, right? Anything, right? So the important thing, like they are like we can generate new things, right? New things that never existed or never existing, right? For example, using generative adversarial networks, we can create or we can generate fake faces. And the specialty is that that face is like not from that face is not from a person who is already existing or existed, right? So that kind of application we can use generative adversarial network. And the other thing is that the GANs are basically implemented and they are discovered in 2014, right? So 6 years back, right? So this is a very new and a fresh topic and categorized under unsupervised deep learning, right? So categorized under unsupervised deep learning. And the other thing is that when we come to like generative adversarial networks, so today the practical session, what we are going to do, we will basically discuss about how to train a generative adversarial network in order to generate handwritten digits, right? In order to generate handwritten digits. So that's the purpose of today's practical session. And before going on to the practical session, let me like quickly recap what we covered on last Saturday, right? The theory part. So then you will be like comfortable with the theory part. So it will be quite easy to uh, start the practical session, right? And so this is the theory part basically. So we have mainly we have two things called the discriminator and the generator, right? So two neural networks are there in the in a normal generative adversarial networks, right? Two neural networks are there, the generator and the discriminator. So these like they are working together, right? Sometimes, and they are like independent sometimes, right? So this is like very, I mean, bit a complex idea, but very easy theory is there. I mean, easy concept is there, but the like it is a bit tricky, as I mentioned last time. So quickly, now what I'm going to do, so first what going to happen, the D network, that means the discriminator network will be trained first, right? So in order to train the discriminator network, uh, what we have to do, yes, so in order to train the discriminator network, what we are going to do, now when you are training the discriminator, so it will be done alone and it will be done independently, right? So this discriminator is basically a neural network which can identify real and fake data, right? Real and fake data. So what we are going to do, let's say like we are going to train a generative adversarial network in order to generate handwritten digits, right? In order to generate handwritten digits, so what we can do, I can my interest is on handwritten digits. So what I'm going to do, I will basically uh, get a data set like 50-50 roughly, right? 50% of my data set will be like real handwritten digits, and the label is not like for those 50%, the label will not be like 7, 8, 9, right? So we are not working with the supervised learning problem. So the label will be 1. So 1 represent like it's a so we have two classes in this neural network that will be 1 and 0. So 1 for real images and 0 for uh, fake images. So what I'm going to do, 50% I'm going to include like they are from real handwritten digits, and other 50% will be like noisy images, right? Noisy images. So random noisy images, right? Randomly generated images. So thereafter, what I'm going to do, 0 and 1. So these 50% will be like labeled as 0, right? So this will be labeled as 0. Then combining those real and fake images, I'm going to create a data set, and this discriminator network will be trained, and at the last layer of this discriminator network, you have a one neuron, and that neuron is basically a sigmoid neuron. And in a sigmoid we are going to get a number between 0 and 1, right? A number between 0 and 1. So that's the, I mean, basically that's what happens in the discriminator network. So we are going to train this, right? So discriminator will be first trained, and that will be done for basically to identify fake and real, right? So now the purpose is like it's like a classification problem, right? A classification neural network, classification type neural network, where we are going to input fake and real. So those will be considered as 1 and 0, right, from the label. And when you are going to train it, and the label will be 1 and 0, as I mentioned. So this neural network is capable of identifying, after it's been trained, the neural network is capable of identifying real and fake handwritten digits. So when you are going to give like a proper written handwritten digit, right? So it will predict like it like 1. And if you are going to input something else like a noise or something else, so it's going to identify it as 0. So the discriminator is basically a neural network which can identify real handwritten digits and fake handwritten digits, or fake data, some noise data, right? Understood. So that's what happens first. So we will be doing, and we will be implementing these things. And first we have to identify is that we are going to train this discriminator, right? So that's what we are going to do first. Then thereafter, what happens, then only we are going to train the generator. So in training the generator, what we are going to do basically, right? When you are going to train the generator, right? And in the generator, basically, you have this kind of a neural network, right? And this neural network is basically uh, like a combined neural network with the generator and the discriminator, right? So this part, now when the generator is trained, so that for that path, the discriminator is also connected, right? And the thing is like we are combining the generator and discriminator, we are going to train the second neural network. I mean, when we are going to, when you are training the discriminator, it's done alone, right? It's done alone. When you are going to train the discriminator, it's done alone for the discriminator, right? So we are not going to combine the generator with the discriminator, right? So when you are going to train it, it will be done independently. But when it comes to the generator training, we are going to combine both the generator and the discriminator, right? And they will be combined. But the thing is, now we are going to freeze the discriminator, right? So we will be freezing the discriminator. That means the weights and the biases of the discriminator won't be updated in this process, right? So basically, we are combining the generator and discriminator in the second step, right? When we are going to train the generator, we are going to combine the generator and the discriminator together and train it. But the thing is, in this case, the discriminator will be freezed, right? So that means like the weights and the biases of the neural network won't be updated. I mean, the weights and biases of the discriminator won't be updated, right? So that's what happens. Then what we are going to do, in the generator, we are inputting some noises, right? So we are inputting just noise, right? It's a small noise, right? And that's a randomly generated noise. And Then this will be, let's say this is going to create a image of 28 by 28, right? Image 28 by 20, and that image will be passed to the discriminator, right? So in the generator what we have, like we are providing a noise, a small noise, and this is going to create a like what kind of image, like let's say 28 by 28 image, and that image will be like, right? So this is generator is not trained yet, so it will be like noisy image. So that noisy image will be passed to the discriminator network, and the discriminator network, since it's like properly trained to identify fake and real handwritten digits, so it's definitely going to predict at 0, right? But here we are going to add the trick, or we are going to do some trick here, that when we are going to train the generator, all the noisy images that we are going to output from the generator will be labeled as 1. That means when you are going to train, I mean when you are going to like provide a noise, and you are going to get again a noisy image, and this noisy image will be trained as 1. But the discriminator is going to say it's a 0. That means it's going to predict it as a fake digit, right? So that this is kind of supervised kind of a learning. So when you are going to provide like the neural network is going to provide 0, and the actual target, when we are going to convert, I mean when we are going to see the actual target, it's 1. So now there's a large error, and we need to minimize that error, right? So I mean the discriminator weights and biases are free, so they won't be trained. So what's going to happen now, always we are trying to minimize the error when we are training a neural network. So what's going to happen, the generator weights and biases will be only the weights and biases of the generator will be updated, since this is freezed. So what's going to happen, these weights and biases will be updated to what, in order to give the output as 1. So that's the only method of minimizing there. So we have a properly trained, well performing neural network in the discriminator, so it's going to identify, no matter what, it can identify real and fake. So in order to get 1 from here, the only method is to provide a properly like I mean a handwritten digit like image from the generator, right? So then only we are going to get, then only we can trick, or then only, yes, then only we can trick the discriminator, right? So generator will be trained in a such a way, like when a noise is given, right? So generator is going to output uh, a real, like like yeah, real looking fake handwritten digit. So then the discriminator will be fooled, or discriminator will be tricked, right? That then the discriminator is going to output 1. So the error will be minimized then, right? So that will be the basic, I mean, right? So that's the basic idea, 2 steps. And thereafter we can get the generator separately. So generator now like is trained to, when a noise is given, it's going to generate a properly written handwritten digits kind of a thing, right? And like for various digits, it's going to provide various, sorry, for various noises, it's going to provide various handwritten digits, like real looking handwritten digits, we can say. Understood? So that's what we discussed on last week. So now we are going to do the practical related to this one, right? Do the practical related to this one. And let me quickly get the code. And so the target is to do what we discussed now, right? Generative adversarial network to basically train, generative adversarial network to generate handwritten digits. So that's what we are going to do in this practical session, right? So quickly I will get uh, the required libraries and others, right? Yes, so yes, so yeah, so let me first get the MNIST data set, right? So from Keras dot data sets, right? Let me, yeah, from Keras dot data sets, right? Keras dot data sets, import uh, import MNIST, right? And then let me get the train data, right? And we don't need the targets. So last time I also explained this, don't need to get the target, right? And then let us get the test data, right? The test data, right? And that's it. Then we can do what M-T load data, right? Load data, right? So that's what we are going to do. And what I'm going to do then, this neural network, sorry, this data set is basically containing altogether 70,000 handwritten digits, right? 7,000 handwritten digits. So simply it's like this. So let me print the the train data 0, and also let me show you like let's visualize the first one. Team show the train data 0, and we can do what we can. Right. Right. So right. So you can see, yeah, a digit of 5. Now that's not what I want to show you. Like you can see the pixel values are in between 0 and 255, right? So the pixel values are in between 0 and 255. So what I want to do here is to like I want to normalize this, right? So we know to normalize the data set before applying it to a neural network. So let me uh, normalize it. And in this case, there will be like, yeah. So I'm going to normalize it between not 0 and 1, but I will normalize it between -1 and +1. So that's how I mean. Usually in generative adversarial networks, we are not going to normalize it between uh, 0 and 1, but we will normalize it between usually -1 and +1. So it could be done easily by applying this expression, right? So can you identify what happens here, right? Basically, when you have, let's say, if the pixel value is 0, right? So if the pixel value is 0, that means 0 minus 127.5 divided by 127.5, right? 127.5. So you know that this will be -1, right? And let's say when the digit is 255, I mean when the pixel is 255, what's going to happen, right? Right. So when you're going to divide, I mean, right, and this will be +1, right? So you can see. So 255 minus 127.5 is 127.5, and when you can divide by 1275, it will be 1. So this will be converted in between 0 and 1. Not see, sorry. Usually, when you are going to normalize, you are going to divide it by 255, and we are going to get pixel values into a range between, we are going to convert it to a range between 0 and 1. But here, for generative adversarial networks and almost autoencoders as well, we are going to convert the data set. If you are dealing with the image data set, we are going to normalize it into a range between -1 and +1, right? I can't exactly mention the reason, but that's the usual thing. I'm not saying that it's not working for like 0 and 1, but it's well performing for -1 range between a pixel range between -1 and +1, right? Okay. Yes. So yeah. Right. So basically, converting it to a range in between, a range between -1 and +1. Then what I'm going to do, like train data, I'm going to reshape it to uh, now what's the train data shape, right? So train data shape basically, right? So let me add the additional row and show you. So this will be 60,028 by 28, right? 60,028 by 28, right? So what I'm going to do now, I will convert this into like reshape it, right? $60,781, right? 84. Right? So what's going to happen? Like we are going to flatten this, right? 28 by 28. We are going to flatten it to 784, right? So we are going to flatten it, right? So like it will be a row vector, right? It would be a row vector. I hope you can remember these things. We have, I mean, you know that we have a 28 by 28 image, and it will be flattened to 784, right? So that means like a row vector, right? So quickly, let me show you here. Yeah. So this should be 60,000, right? Thank you for mentioning it. Okay. Sorry for the delay. And so what I wanted to show you, right? Here we have basically we have a data set with 60,000 images, and all of them are like 28 by 28, right? So we are going to flatten it. I hope you all can remember what's flattening, right? So it's like 28, 28, right? So like likewise, we have 60,000 images, right? 60,000 images are there, right? So they will be basically flattened into, right, this kind of like 784, right? Each image will be flattened, right? Likewise, each image will be flattened into 784 1D vector, right? 1V row vector we can see, right? So that's what happens. And after that, what I'm going to do, so that's yeah, so that's pretty much everything that we need to do here. And the labels are not going to be a matter. We don't know, I mean, we are not worried about this is 5, this is 6, or this is 7, or this is 8, whatever, right? What we are looking for is like, what we want is basically we want uh, a real and a fake digits, right? So that's what we want, right? And let me run this quickly, right? So we have create the data set, and then thereafter yeah, so then let me create the generator. Right? So let me create the generator network. So before creating the generator network, let me basically get the required libraries and the dependencies. I'm going to get the Keras layers, import input layer, and then from Keras, so from Keras dot models, uh, Keras dot models, import yeah, import model and sequential model, right? So both will be imported. Now, can you remember this model? We use this in the autoencoders that when we have like two neural networks, we can combine them using like the input and output layers, right? So that model will be also imported here. And after that, right, uh, from keras.layers, right, import dense dropout, dense dropout, right? Those layers will be imported, and thereafter uh, from keras dot layers and advanced activations, we are going to get leaky relu. Now, hope I don't know whether you can remember the leaky relu activation, but I will anyway explain the leaky relu activation in a bit when we are using it, and that's pretty much everything. So we can get the Adam optimizer as well. Import Adam, right? So Adam optimizer, and so that's pretty much everything. And one last thing I will explain, like the new things when we are using them, right? The initializers will be also included here. So these are the main things that require for implementing the neural network architectures, right? And thereafter, what I'm going to do with the required libraries, I'm going to define the generator, right? The generator network, right? The generator network will be first defined. So it will be a sequential model. We are familiar with sequential models, and let me add layer by layer, right? So if it is a sequential layer, we can always add layer by layer, right? Using model.add. So let me add a dense layer first, dense layer, and this will be 256 neurons having. So keep that thing in mind that I'm going to like define the generator and the discriminator separately, and later I can combine them and create the generative adversarial network today, right? So you know, in the GAN or generative adversarial network, we have the generator and the discriminator. So we will create them, or we will define them separately, and we will be combining them for obtain the obtain the uh, obtain the generative adversarial network, right? And now the generator, what I mean by the generator here, you can remember the generator. Uh, this is the generator, right? This is the generator. So for the generator, you can see clearly uh, the generator noise will be the input, right? A noise will be the input, right? A small noise will be the input for a generator, right? So for this, we will be using like a noise of, right? So this is the generator. So it will be a noise will be the input, and output will be a handwritten digit, right? A handwritten digit, right? See, right? So it's generated. And what I'm going to do here, so basically we can, uh, I'm going to add the first hidden layer, and the input dimensions for this neural network will be given let me define noise dimension, a variable called voice dimension. So it will be 100 basically, right? And uh, okay, so then input dimension will be uh, yeah, input dimension will be uh, basically 100 by 100, or we can let me quickly check the random dimension, whether it's a two-dimensional or one-dimensional. Yeah, so we can give the noise dimension as the input dimension here, right? So we are going to basically do it like this, right? We are going to do it like this, right? So getting, we will be giving a noise of 100, right? And the generator, right? The generator will be providing us a what, right? A 784, right? So later what we can do now, this will be like, we can convert actually the 784 means a flattened version, right? So this is a flattened version, but actually we can convert it to a, later we can convert it to a, right, 28 by 28 image, right? And also uh, like this is to be like 100, but actually we can see it as what, we can see it as like 10 by 10 2D, right? So actually 10 by 10 2D. So this will be like actually flattened, and we have 100 uh, noise of 100, and here also we are getting 784 values, but we can convert it to a two-dimensional thing, right? Okay, so that's it here. Then what we can do, so we have the models initialized, right? And yeah, so that's pretty much everything. And then let me add uh, a leaky ReLU activation. A leaky ReLU activation. So this is a very important thing to be noticed, that we are going to use leaky ReLU I mean, instead of ReLU activation, we are going to uh, like most of the times we are going to use leak ReLU. So what do you mean by leak ReLU? So you know ReLU, right? So ReLU activation is something like this. You can remember the ReLU activation. I hope you all can remember like this, right? So this is uh, the right? This is the Z, and this is the Y, where Y equal F Z, right? You can remember, right? So in leak ReLU, what it means, right? So this is leak. So this is ReLU. Right? This is ReLU. This is ReLU, and this is leak ReLU. The same thing here. Like it's not like this, but it's like this, right? So it's like having a slope of 0.2. I mean 0. Like here it's y z, y equal z. Here it's like y equal a z, y equal a z. For example, it's like y equals 0.2 z. right? Understood. So that gradient is given here, right? The gradient is given here. Okay. So please ask any question you have, if you have any questions, right? Okay, so then leaky relu and is added here. So thereafter, what we can do, I'm going to add another, right, another dense layer, a dense layer of 512, right? Let me add the dense layer of 512, and again a leaky relu, the activation function, the leaky relu activation, right? And another dense layer. So you can see kind of a decoder kind of architecture now. What I mean is the size is increasing, right, eventually. So then like this, I mean, these are just random numbers. I mean, the size of the generator, the number of neurons, they are random, right? The size is randomly added. And finally, the output layer. So can someone tell me what's the, like how many neurons there should be in the output layer? So I'm going to finish the neural network from here, the architecture from here. So can you, yes, good. Let's see. No, here we are like we are focusing on the generator, right? Not the discriminator. So this is generator, the generator network. Yes, I told you, like we are creating separately, right? Generator separately and discriminator separately. So what will be the output of the generator? Yes. Shall I give you a yes? So see, yes, good. So it will be 784, right? 784. Sorry, yeah, 784. Then the activation bit confusing here, but the activation will be used as a tan activation. Why we are going to use tan activation? Can someone guess? Yes. What's the purpose of using tan activation here? Yes. Why? Now, can you remember? Like we converted. Yes. Right. So good. Uh, we convert. Can you remember? The we converted the images into a range between -1 and +1. Can you remember? Right. So here, right. So the output from the generator should be also between minus and 1 plus 1, right? -1 and +1. So only way to get that is using a TARN activation. So can you remember what do you mean by TARN? Now these are basics, right? So these are basics which we covered them in like the initial part of the course, right? So in TARN activation, you will having something like this. +1 and -1, right? TARN activation, right? Got it. So what I'm going to do now, so that's why we are using TARN, right? Right. Okay, so binary cross entropy. So what I mean by binary cross entropy, like for values between like two values -1 +1, or like 0 and 1, they are using binary cross entropy. Hope you can remember. And the optimizer, right? The optimizer. Uh, so here we are using optimizer. The Adam optimizer will be used, right? And the optimizer. Uh, uh, yeah. So let me define optimizer here. So optimizer will be the Adam optimizer, but here a bit different, like Adam, and we are going to initialize the learning rate, right? The learning rate can you remember what's learning rate? In the third week probably, the learning rate we can initialize, and also some parameter called beta 1. I will explain what I mean by beta 1, right, in a minute. But without using the Adam optimizer, like the default Adam optimizer, I'm adding a customized learning rate here, right? Like how to decide this value. Uh, Now, according to the training, right? So if the training is not going well, or the results are not going well, we can change these learning rates and see like what will happen when we are going to input the optimizer like this. Then it's going to like use the general Adam optimizer. That means like all the learning rates and all the decaying rates, all the things will be set to their defaults, right? But here we can customize our own Adam optimizer. That means we can have our own learning rate. We can have our own beta 1 values. I will explain what mean by beta, right? And I'm creating my own customized optimizer, and that will be uh, given here as the optimizer, right? Right. Okay, so with that I can conclude uh, the generator, right? So basically generator is a decoder, kind of a decoder, where it start from 100, right? So input will be 100, right? Or else we can consider it at 10 by 10. Then you have 256 neurons, 512 neurons, and 1024 neurons, right? And the last layer will be 784, right? The last layer will be 784, or else we can consider it as 28 by 28 image, right? So let me run this and see whether we are getting any errors. Yes, we have. Yeah, not here, like, and not and, comma should be there. Yeah, that's a spelling mistake, I think. Sequential. Let me clear these things. uh okay, so there's something called advanced activation. Let me quickly. Yeah, so it should be advanced activations. Leaky relu. Uh, yeah, I don't need this actually here. Yeah, so with that, it's compiled without any issues, right? So this is generator architecture. Right? The generator is created already. Then let me right. So create the discriminator, right? So see, so we have created the generator and it's done. So now let me create the discriminator. Discriminator, right? So discriminator also will be a sequential type neural network. a sequential type neural network. And let me add a dense layer first. Okay, so now before creating the uh, discriminator network, I want to show you something, right? So this is the discriminator. So can you imagine the input and output, so then it will be easy, right? So input will be what? For the discriminator, input size or input dimensions will be good 784. The output, the output, yes, 1. Good, right? 1 or 0. I mean, no two classes are there, only one neuron is there, that's giving 0 or 1, right? Simple. Good. Now let me add the first hidden layer, right? First hidden layer. So dense layer will be added, and I'm going like, you know that the discriminator is bit kind of uh, encoder, right? So we are going to start with the larger dimension and eventually reduce the size, and we are eventually at the end we are going to get 1, right? Size එක පොඩ්ඩ අඩු වෙලා එක වෙන්න තමයි එනතර ලොකු එකකින් පටන් ගන්න පොඩ්ඩ අඩු වෙලා එන්න ඕනේ, right? Now don't think that not like the autoencoder, right? So these two won't be mirror images, right? These don't two won't be mirror image, right? No need to do it like that. In the autoencoder there's a requirement, actually that's also not a requirement, but in the autoencoder we build the autoencoder like that, right? Like the encoder and the discriminator are mirror images, right? But here in the GAN or the generative adversarial network, it's not necessary to be a mirror image, but generator is kind of a decoder and the discriminator is kind of a encoder, right? No need to like be mirror images, right? And the input dimension, so as you mentioned, it will be 784, right? 784. And then with that we can again add the leaky relos, right? මේක අනිවාර්ය මත තියන්න mirror image එක වෙන්න ඕනේ කියලා නීතියක් නැහැ, right? මේ වෙන්න ඕනේ කියලා කියන්නේ නැහැ, right? And here now actually this is a tuned neural network, right? So what I'm doing implementing with you is a already checked, already trained neural network, right? So don't think, okay, how you are going to get this 256, how we are going to get 512, how we are going to get 1024, and how we are going to get it like leaky relu. No, we can't think it at once, right? Also we can't think it at once. Actually this is, as I mentioned from the first week, as I'm mentioning from the first week, this is kind of a trial and error thing. That means you need to have a theoretical knowledge. This is not random, I mean completely trial and error. But what I want to highlight here is that this is basically like you have to have a knowledge, you have to have the basics. With that, it's bit you have to check with this, you have to check with dropout layers. If it is overfitting, you have to do something else. Likewise, this is always trial and error. You have to run it again and again, see and get the best results. So you have to do some fine tuning, right? So I'm going to add dropout layers here as well. මම මේ කිව්වේ ඔයාලට මේ එකපාර මම මේ දාන්නේ කොහොමද කියලා ප්‍රශ්නයක් එනවනේ. ඒතර ඒකට තියෙන එකම දේ තමයි මේක. ඉතින් අර මම අපි ෆයින් ටියුන් කරපු එකක්. එතකොට එකම දේ තමයි ඒක කරන්න. ඉතින් පොඩි තියරි අපි තියරි පාවිච්චි කරලා නියුරල් නෙට්වර්ක් එකක් හාලා ඒවා බලලා රිසල්ට්ස් එන විදිහට රිසල්ට්ස් හොඳ නැත්නම් තව ටිකක් වෙනස් කරලා ඒ වගේ පොඩි ඉන්වෝල්ව්මන්ට් එකක් තියෙන්න ඕනේ, right? නැතුව හැම නියුරල් නෙට්වර්ක් එකම නිකන් ඔහේ දාපු ගමන් රිසල්ට්ස් එනවා නම් වැඩක් නැහැ නේ. එහෙම එන්නේ නැහැ, right? So you have to do your work, you have to do some fine tuning. And Yeah, so these should be like discriminated. And yeah, so I think it will be better if we, yeah, okay. File to error, and the same thing will be added. Now, I'm not saying, right, don't get the idea wrong. I'm not saying that my model is the best model. Sometimes you may come up with a better model, right? So that's always there, right? Don't think that this is the only method to generate handwritten digits using generative adversarial networks. No, right? So I'm just saying you this is something already test and fine tuned. Again, මම මේ හදන network already trained and a fine tuned network. You have to like play with these things, right? So don't think, as I mentioned, that's why I'm always telling this now. I'm very disappointed about that attendance, right? So I don't know what's the reason. What I think is most of them, right? So who are like currently missing the live sessions, right? So most of them most probably have like missed 1 week due to some reason. I'm not saying like it could be a genuine reason, right? Right. So with that, let's say, okay, so if you are going to miss the theory part, the, the Saturday's lesson, then probably you won't attend the Tuesday's lesson, right? Now, if someone is coming today without participating on Saturday, right? So it's almost like what? It's almost useless, right? You can't understand what's discriminator, what's the generator, right? So if you are going to miss one Saturday, then you will probably you have to do nothing. You have to miss the uh, Tuesday session as well. Sorry, yes, Tuesday session as well. And thereafter, like sometimes now, autoencoders and generative addresses might be get connected, right? So then you will also miss the next Saturday. Likewise, you are going to then think I'm going to watch the video and come, right? That's not going to happen most of the time. So you are lagging, and sometimes we are going to end the course, right, with you all, and others might be like 5 or 6 weeks behind. I don't know whether they are going to finish this by watching the videos, but I can't do anything about that, right? So what I want to highlight is you have to spend time with this, right? Otherwise, like just paying and like, okay, I'm participating in a neural network and deep learning course, so that won't do anything, right? You have to do your own work. You have to search, you have to do your own work, you have to spend time with this. Otherwise, it won't be effective, right? So keep, I mean, for you all, right, just participating this course won't give you anything, right? So you have to work on this. You have to work your own, I mean, you have to do your own work. You have to play with these things, right? And the other thing is that, as I mentioned, after finishing this course, don't think that you are expert in deep learning or neural network. You are just a beginner, right? What you have is you have a good foundation, right? So this is where you are going to start learning, right? So we are going to break the ice, and we have a good foundation, and we are ready with everything. We have the implementation knowledge, we have the theoretical knowledge, everything is with there, right? Everything is with us. So this is where you are going to start. This is where you are going to start your projects. This is where you are going to start your research. This is where you are going to start your practical implementations, right? So finishing this course, right? So it's not means that you have all the knowledge regarding this. No, this is a right heavily updating field, right? So it's updating day by day. Now what we are discussing today is something happening like 6 years back, so very fresh theories, right? So please do your work, please spend time with this, right? Otherwise useless, otherwise not effective, right? So the last layer, I'm going to add the last layer, right? So the last layer will be one neuron, right, with the softmax activation, so the sigmoid activation, and that will be like this. So I can add the activation here as well. So it will be sigmoid activation. Right? Here should be dense. Right? Activation sigmoid, yes, that's it. And we need to compile this as well. Right? Right? The discriminator will be compiled using the binary cost entropy loss. And the same optimizer will be used. Right. So yes, so that's pretty much everything. Right. Yes, so okay, right. So what we are going to do now, we need to first train the uh, right. So we need to first train it. The discriminator should be trained, right? So right, the discriminator should be trained, and yeah, right. So what we are going to do now, we have the generator and the discriminator separately, right? So we need to now, according to our theory, what we learned on last times, right? We have to, right, step by step, right? So we have to train it, the generator and the discriminator, right? So we have the both neural networks ready, right? So we have the both neural networks ready here, and uh, uh, so we need to get it from the generator, and yes, so the discriminator, we will be training it first, as I mentioned. There's a small modification, I mean, not the modification, but a small difference here, that in this case, we are doing it like epoch by epoch, right? We will be training it by epoch. So it's like, yeah, so yeah, for E in range, uh, okay, let's do it for 400, and yeah, for in range 400, right? So this loop will run 400 times, right? And what I'm going to do now, uh, I'm going to create something called batch size, right? Batch size, and like we can use a batch size of 128, right? 128. I will explain what we mean by batch size, and then the batch count. I'm going to get something called batch count, right? Batch count, and it will be basically batch count will be basically integer. Like we are going to get the train data dot shape 0. That means 60,000. You know what, right? Train data dot shape 0 is 60,000, and it will be divided by batch size, right? It will be divided by batch size, and so I will show you what's batch size, batch count then, right? Batch count then. So it will be basically 468, right? 468, and this will run 400 times. This will run 400 times, and then there will be another loop inside the there will be another loop inside uh, this, right? So let me call it like I, for I in range batch count, right? So it's like this. I will explain this batch count now. So you know that we have a outer loop which will run 400 times, and we have another inner loop which will run for 468 times, right? So this is basically batch count will be equals to 468 times, right? 468 times, right? Simple, right? So for each run of this outer loop, this will run 468 times. මේක එකපාරක් යන මේක එකපාරකට මේක 468 වතාවක් run වෙනවා, right? For like one instant of this loop, the outer loop, 460 times of the inner loop will run, right? So I will explain what this batch count and what's the batch size. But before going on to that, let me first get some random noises here, right? Then I will explain you what happened. Random, normal, random normal, and the values will be between 0 and 1, and size will be batch size, and random dimensions, right? So what's going to happen, like the noise will be basically in between 0 and 1, right? So that's what it means. The noise we are going to create will be between 0 and 1, and the size of that array, so this noise will be an array, and the size of that will be batch size random dim. So that, sorry, not random dim, noise dim. This should be noise dim, right? So what you are going to do basically here, so noise will be equals to, right? Noise is equals to like something like this, 100, right? So noise CE noise මේ අපි හදනවා කියේ. ඒ CE noise 128ක් අපි හදනවා. So this is a batch. 128 batch එකක් අපි හදන්නේ. Right? 128ක් noise. 128 batch එකක් අපි හදනවා. Right? Right? Oh, let me like get it like no, yeah, it's fine. And then so these are like we have 1 to 8 noises, and also real images, real images batch. Real images. Yeah, real images batch. Real images batch. So real images batch will be from train data. I'm going to get yeah. Yeah. Train data, right? So here it's a bit tricky. np dot random integer, and this will be basically random integer and 0 to 60,000. Yeah, so train data dot shape 0, and yeah, so then the batch size will be yeah, batch size. Right. So now I don't know whether right. So right. So here, what we are going to do, right? So we have now. I hope that you can you can understand this one, right? So it's equals to random normal 0 and 1 size, batch size equal noise dim. So here what's going to happen? Now we are going to create 100, right? We are going to create 100, right? Again, we are going to create 100. Size will be 100, and they're going to create 180 of them, right? CA ඒවා 128ක් හදනවා. ඒ වගේ තියෙන values ඔක්කොම තියෙන්නේ 0.1 අතර තමයි මෙතන තියෙන values. මේ 100ක් තියෙනනේ values. So those 100 values, all the values will be between 0 and 1, right? Not 0 and 1, they will be in between 0 and 1, right? 0 and 1, that means like values can be there like 0.1, 0.25, 0.3, 0.9. Likewise, values can be there like that, right? So that's what you know. And here there's a bit tricky thing here, right? There's a bit tricky thing here. This one, right? Okay, real image batch will be equal to train data, right? np dot random integer, this one. So shall we first check what this is, right? මේක පොඩ්ඩක් අපි බලමු ඉස්සෙල්ලා මොකද්ද මේකෙන් කියන්නේ කියලා. Right. Okay, so can you see now? We will read this separately. np dot random integer 0 train data dot shape. So if you like substitute numbers here, if you substitute numbers here, like this is 0, this is 60,000, right? And size equal like it will be 1 to 8. Batch size is 1 to 8, right? You can remember the batch size is 1 to 8, right? Batch size එක 1 to 8 නේ අපි දැම්මනේ උඩ, right? එහෙනම් මේවා එකක් තමයි තියෙන්නේ. මොකද කරන්නේ? මෙයා 0.60000 අතර integers නේ. Can you see integers? 0.60000 අතර integers 128ක් තියෙන array එකක් තමයි මෙන්න මේකෙන් හදලා දෙන්නේ අපිට. ඒ කියන්නේ simply 0 ඉඳන් 60000 දක්වා numbers ටිකක් randomly select කරලා දෙනවා 128ක් numbers. So you can remember np.random integer. So this is the minimum, I mean this is the lower limit, right? This is the minimum and this will be the maximum, right? And 1 to 8 numbers. මේ දෙක අතර 0.60000 අතර නම් 128ක්, right? So ඒක තමයි මෙන්න මේ np.random integer එකෙන් වෙන්නේ. Right? So those random, we have like 1 to 8 random numbers, and those will be like what we are going to do here. See, we are going to now again, so keep this idea, right? np.random integer 0 train data shape size equal batch size. So this will give us 1 to 8 numbers, and sorry, 1 to 8 numbers, and those numbers are in between 0 and 60,000. That's it, right? And here what we are going to do, right? Here what we are going to do, those 1 to 8 numbers, right? We are going to get here the මේකෙන් දෙන්නේ ඕකනේ බිංදුව ඉඳන් 60000 දක්වා අංක 128. අන්නේ 128ට අදාළ trend data වලින් තියෙන images ටික අරගෙන ඇවිල්ලා මෙන්න මේ real images batch කියන එකට දාගන්න. Understood? So we are going to generate some random numbers in between 0 and 60,000, and those will be like 1 to 8 numbers, right? 1 to 8 numbers, and images corresponding, right? The corresponding images for that numbers from the handwritten digits will be extracted or taken here. අන්නේ randomly ගන්න 128 දැන් තියානේ එන්න පුළුවන්. දැන් මෙතන මේ numbers ටික තියනවා. මෙයා මොකද කරන්නේ? මේ අපි ගාව 60000ක් තියෙනවා. 60000න් එයා තෝරගන්නවා 29000 25 48805 34703, right? ඔන්න ඔය වගේ 128ක් images තෝරගෙන මෙතන දාගන්න. So it's like we are selecting 1 to 8 images randomly from the handwritten digits, that 60,000 handwritten digits. Simple, right? එහෙනම් අපි ගාව noise 128ක් තියෙනවා, real handwritten digits අර 60000න් ගත්ත randomly set කරගත්ත 128ක් තියෙනවා, right? So that's what we have, right? So then what we are going to do, right? From these noisy images, right? So from these noisy images, what we are going to do, these noisy images will be passed to the generator network. Right? So here, those, like we have 1 to 8 noises, those noises will be passed to the generator network. Now, what you have now, think now, the generator neural network is not trained yet, but here we are going to do it, right? The neural network is not trained yet, but what we are going to do, we are going to like get something like this: generator dot predict generator dot predict, and we are going to add this noise, we are going to pass this noise, right? So what happens? So generator, yeah, I know that generator is not trained yet, right? Generator is not trained yet, but what we can say, right? So when we are going to give noises, it will generate some fake images, some noisy images, right? I'm train කරලා ඉවර නැහැ. ඒත් මෙයාට ඉතින් දුන්නා මොකද වෙන්නේ? noise දුන්නා මෙයා මේ වගේ fake ටිකක් generate කරලා දෙනවා, right? So here we are going to get these as what? Fake images batch or fake image batch. Got it, right? So what you are going to, okay, we have like 1 to 8 real images, 1 to 8 fake images, right? And then we have 128ක් real images තියෙනවා, 128ක් noisy images තියෙනවා, right? So then what I'm going to do, right? Then I'm going to do what? Data equal numpy dot concatenate real image batch, fake image batch, right? Real image batch, fake image batch, right? So I'm going to like what? I'm going to concatenate the real images and fake images. So what we have like now 128 real images, 128 fake images. So it's like, so data is like what? 256 images, right? Then the data එකේ තියෙන අර දෙක එකතු කරපු එක 256 images, right? Okay, so target, I'm going to do it like this. Target මම ඔන්න training data set එක මම හදනවා. real images 128යි fake images 128යි. target කොහොමද දෙන්න ඕනේ? Yes, can you, I mean, now this data set is, I'm creating this data set to train the generator, right? So I'm sorry, to train the discriminator. So I'm creating a data set to train the discriminator. So in the data set we have like 128 real, 128 fake. Now what will be the labels of them? Yes, good, we have answer. Let's see. 0 and 1, good. 0 and 1, right? 0 and 1, okay. But what are 0, what are 1? Right? So it's like this, right? It's like this. Now the data is like we have real images like this, right? And like first 1 to 8 will be, right, this kind of images. Then the other, right? So here to 256 are fake, right? So this is data, and I need what target is. So these are what? These should be 1 and these should be zeros. එහෙනම් පළවෙනි 128 එක කරන්න ඕනේ, දෙවෙනි 128 කියන්නේ 128 ඉඳන් 256 දක්වා බිංදුව කරන්න. Right? So let's check whether those are the answers you have given. Yes, real one, fake one. නේද? එහෙනම් පළවෙනි 128 දැන් අපි මේ දෙක concatenate කරලා එකට එකතු කරලානේ හැදුවේ data කියන එක. එහෙනම් data එකේ පළවෙනි 128 එක වෙන්න ඕනේ, දෙවෙනි 128 බිංදුව වෙන්න ඕනේ. So what we can do? Target, right? Target will be np.zeros. So I'm going to create twice the batch size number of zeros. 128 ගුණ කිරීම 256ක් බිංදු තියෙනවා කියලා මම හදනවා. එහෙනම් දැන් මේක ඔක්කොම 256න් බිඳු වෙනවා, right? 256න් බිඳු වෙනවා. ඊට පස්සේ මම මොකද කරන්නේ? මේකේ අවසාන ටික මුල් ටික, yes, අවසාන ටික පළවෙනි ටික බිඳුවේ ඉඳන් batch size එක දක්වා. ඒ කියන්නේ 128 දක්වා. Right? So this will be what? This should be yes, the first 1 to 8 should be this should be 1. Yes, exactly, right? But the thing is now I'm not going to usually these won't be 1, right? These won't be 1. Like we are going to what? We are going to we are going to actually set a bit less number than 1, right? Bit less number than 1. Can you imagine the reason? Can you imagine the reason? That means like this. We are not saying, okay, these are the perfect handwritten digit. These are also like not one. These are 0.9. So that means what? Like neural network එක train වෙන්නේ මේක කියලා හිතාගන්න මේක 0.9 කියලා හිතාගන්න. ඒ කියන්නේ සමහරවිට generate එක මීටත් වඩා එහා හොඳ ඒවා අපිට දෙන්න පුළුවන්. So it's going to see like, okay, these handwritten digits are not one, but they are 0.9. So when the generator is trained, it can give more than like it's training like to give more like good images, right? So good images than the MNIST data set. So that's why usually we are going to put it like a less number, not one, right? So now with this, I'm going to do something like this, right? So I forgot one thing. So I want to like add another one and get the GAN, right? GAN network, right? Or like, yeah, GAN. So GAN will be basically I want the GAN, and the GAN will be basically uh, uh, yeah, GAN. The input for the GAN will be input shape, right? GAN එක ගත්තාම input එක එන්නේ මොකද්ද? For the GAN, what's the input? So this is the GAN. What will be the input? So this whole thing is the GAN, right? This whole neural network is known as the GAN. So we have the discriminator and the generator separately. So what do you mean by GAN? The whole GAN is this whole image. So what will be the input for the GAN? Yes. දැන් discriminator එක generator අපි දෙකම හැදුවා. දැන් GAN එකක් කියලා කියන්නේ generative adversarial network කියන්නේ මේ දෙක combine කළාම එන එක. So the combined model, what's the input? What's the input of the combined model? Yes. Anyone? GAN එකේ input එක මොකක්ද? GAN එක කියන්නේ මේ දෙකම කියන්නේ GAN එක කියන හැට මේ වගේ. Right, so GAN is like this. So this is what you call the GAN. So you can see, right? You can see, right? This is the input for the GAN. And this is the output of the GAN. Right? So basically, yeah, input will be 100, right? So input will be 100. I noise එකක් නේ අපි එකපාරට දෙන්නේ. Noise එකක් කියන්නේ 100 නේ size එක. එහෙනම් input size will be 100. Input size will be 100. Yes. So the input size will be 100. So here GAN input shape will be random dim. Sorry, not random, noise dim. Noise dim. Noise dim. And right, so GAN input and the layer one. What the layer one? Let me do like GAN layer one. What will be the GAN layer one? Now see what the GAN layer one එක වෙන්නේ. මෙයාගේ පළවෙනි layer එක තමයි generator එකේ පළවෙනි layer එක තමයි GAN එකේ layer එක වෙන්නේ නේද? පළවෙනි layer එක. GAN එක පටන් ගන්න මම කියවනේ මෙතනින් පටන් ගන්න. Right? So GAN layer one will be generator model mother. Can you remember autoencoder, how we created the neural network? This is also that method. We are following that method, right? And GAN output will be like discriminator. අර මම කිය multiply කර වගේ හදනවා කියලා model එක අපි auto encode වල හැදුවේ, right? So that method, right? So then hello everyone, sorry about the disturbance. There was a power cut, right? But now it's fine. And yes, so yeah, so the input and the output are declared. So what we can do now, we can get the generator network, right? The generator model, let's say, or let's say GAN, right? GAN. So we can create the GAN using the model. Now, if you are not understanding what I'm doing here, please refer the method that we followed in order to create the autoencoder, right? Create the autoencoder. Create the autoencoder in last practical session, right? So the same method is followed here to create the GAN as well, right? But the discriminator and the generator were created using the normal sequential method, but here I'm using a different method to create the method that I use for autoencoders here is used to create the GAN as well, right? So inputs will be equals to the GAN input, and the outputs will be equals to the GAN output. So here, like we creating the input and output, we can define the generative adversarial network, right? So we have used the input will be a noise. So you can remember the input is the noise, output is the output of the, right? So you can see output is the output of the discriminator, right? Discriminator के output එක තමයි output එක වෙන්නේ. Input එක වෙන්නේ noise එක, output එක වෙන්නේ discriminator के output එක. So the input is the noise, output is the output of the discriminator, right? So here you can see the GAN output is declared, and using the input and output, finally we can create the generative adversarial network, right? So then after this we have to compile it, right? So we have to compile it using compile, and we have to define the loss function, right? So loss will be basically equals to the binary cross entropy loss, binary cross entropy loss, binary cross entropy loss, and it will be right like this, and the optimizer, right? So we have to give the optimizer then, right? The optimizer, so optimizer will be equals to optimizer, right? And that's it, right? So the binary cross entropy and the optimizer, we have to define the GAN separately. So now here is a bit interesting thing. Now we have trained we have defined the generator separately, discriminator separately, and the GAN, combining those two, like input and output, we have created the GAN as well, right? So now what we are going to do here, now we are going to train so we have a data set with real and fake. Now first, you can remember what we was discussing on last time. We need to first train the discriminator, right? We have to first train the discriminator. So now using this real and fake images, I will be training the I'm going to train the discriminator, right? So discriminator will be trained here. So this is called batch training. I will explain that, but let me do it like this, and I'm going to make the discriminator, right? The discriminator, I'm going to do it like this: trainable equals true. That means what? I'm going to unlock the discriminator. That means I'm going to defreeze, like not freeze, defreeze the discriminator. Discriminator का defreeze करना है ये. अब ये का trainable true करना. So that means what? Trainable, making trainable true is like, okay, now discriminator is free to train, right? මේක කලින් නැතත් ප්‍රශ්නයක් නැහැ, but I will explain what the importance of making it true here, right? And then what I can do, yes, discriminator dot train on batch, right? So here we are following the batch training, and I'm going to get data and target. I'm going to give data and target, and then so here this will be basically training the discriminator. Right, so the discriminator is trained, right, and for one epoch, right, so only one for one epoch. So we can give it like epochs equal 1, or else you can keep it like this, so it will be like trained once, ekapara training only once, right? So then I'm going to after training it, I'm going to train the generator, right? Train the generator, right? Train the generator, right? So generator will be trained now, right? Give me a second. Okay, so now I'm going to train the generator. Now, can you remember when we are going to train the generator, we need to right, lock this, right? So we need to lock this. That means we have to freeze it, right? So generator will be freezed here, right? So the generator will be trained, and what we are going to do, right? So the discriminator trainable, right? So the discriminator trainable will be set to false, right? So it will be set to false. That means now in this process, after this, after training the discriminator, we are going to freeze it. Now the discriminator is no more trainable. That means the weights and biases will not be adjusted, right? Weights and biases of the discriminator will not be adjusted anymore, right? After this point, right? So we are going to make it false. Then the GAN will be trained here. The GAN, I'm going to train the GAN, right? So you can see we can't train the generator separately, right? So we can't train the generator separately. So the whole GAN should be trained, right? So whole GAN should be trained, and okay, so then the whole GAN will be trained. So we are going to train the GAN. So this part should be, now we can't train the generators, right? So we can't train the generator. We have to train whole the GAN, right? So keep that thing in mind. After generator train can be, what happens, like we have trained GAN, and when you are going to train the GAN, we have to freeze the discriminator. Like when you are going to freeze the discriminator and train the GAN, after that, after training, we can use the GAN separately for generating new samples. You know, like discriminator එක වෙනම train කරනවා. ඊට පස්සේ generator එක වෙනම train කරන්න බෑ. GAN එක තමයි train කරන්න ඕනේ. GAN එක train කරලා discriminator lock කරනවා. ඊට පස්සේ train කළා ඉවරනාට පස්සේ අපි generator ගලවලා අරගෙන generator එකෙන් තමයි අපි predictions ගන්න. I mean generate කරන්නේ, right? So here this is where you are going to like freeze the weights, right? Freeze the right? Freeze the trainable parameters, right? Freeze the trainable parameters, right? Understood? Uh, yeah. Uh, okay, right? Uh, okay. Yes. Right. Okay. So then what you are going to do, train the GAN, right? So we have trained the GAN, and GAN will be trained basically. Uh, that's also will be trained on batch, right? Train on batch. I will explain what you mean by train on batch, right? Later. Uh, I'm going to train it, right? And can you tell me, yes, for training the GAN, what will be the input and the, I mean, the data and target? To train the GAN, what will be the data and target? Yes, noise and target. Yes, good. But the thing is now we have like generate some noises here. I can input then the noises can generate kind of. So noises. Uh, I'm going to generate another noises, right? A set of new noises, right? So it will be generated using the same thing, and right. So the earlier noise was generated like train the discriminator. Now for the GAN, we need to uh, create another, and so this will be the data, right? Data for the uh, GAN, and what will be the target for the GAN, right? What will be the target for the GAN? Data නම් හරි noise නේ, target එක මොකද්ද GAN එකේ? Yes. Yes. Target මොනවද වෙන්නේ? Noise එකේ දැන් අපි ජෙනරේටර් එක ට්‍රේන් කරන්න කියලා අපි GAN එක තමයි ට්‍රේන් කරන්නේ. GAN එක ට්‍රේන් කරලා අපි ඉන්පුට් දිහා noise ටිකක් දෙනවා. ඒක target එක මොකක්ද? Target එක මොකක්ද? Yes. What will be the target? Good. Let's see. We have an answer here. 0 and 1. Others. What about others? What do you think? Yes. Can I remember this? The actual target is always 1. ඇයි අපි noise දීලා යාට by force කියන මේ එන්නේ 1 කියලා. අපි noise දීලා මෙයාට කියනවා අපි මේ එන්නේ ඇත්ත images කියලා. noise එකක් දුන්නාම generator එකෙන් our noise image එක generate කරනවා. ඒක අපි 1 කියලා කියන්නේ by force. නේද? මතකද? right? අපි මොකද යාට කියන්නේ යාට තේරුම් ගන්න අපි කියන්නේ ඩිස්ක්‍රිමිනේට් එක බින්දුව දුන්නා අපි කියන්නේ නෑ මේක එකක් කියලා. එතකොට ජෙනරේට් එක තවත් ඉම්ප්‍රූව් වෙලා එක කරන් try කරන්නේ ඒක. Right? Understood. So here the targets will be should be 1. np dot ones like equals to batch size. Right? Because you see attack other no ones, right? So we have to train them then on on them, right? Right? Yes, so that's it, and that's pretty much everything, right? So we will basically plot the outputs, right? Like if I is yeah, I equals like I equal 0 or I equal like every 20 epoch, right? Right, for every 20 epoch I'm going to plot the outputs and see, right? So how to plot the outputs? uh, so did we, yeah, we have implored the matplotlib, right? So for the 0 epoch and the I mean all the 20 epoch that we are getting the remainder here, right? Again we say gunakara වලට එනකොට මේක බිංදුව වෙනවනේ. So all the 20 epochs, I mean all the like for each 20 epoch from the 0 and then 20, 40, 60, we are going to plot some samples and see whether we are getting right, correct, like what's the result, right? Okay, so noise, I'm going to create a noise, right? Now after each training what I'm going to do, like for each 20 epoch I'm going to do this. I'm a epoch 20කට මම මේක කරනවා, right? So I'm going to check what are the outputs given by the trained generator. So I'm going to create some random noise and input them and see what are the outputs given by the generator, right? I'm a training එකටම පළවෙනි training එකේ 20 වෙනි epoch හැම epochs 20කට වතාවක් මම noise ටිකක් දාලා බලනවා මොනවද මෙයා generate කරන images කියලා, right? So noise again, like we can yeah, we can create some, like we can create some like 100 samples, random dot random normal, right? Normal and like 0 and 1, and then the size will be equals to, like we are going to create 100, let's say 50, yeah, 50 like noise dim, that means for like CA noise එක dimension කියන 50 noise dimensions හදනවා 50ක් noise dimensions CA 50ක් හදනවා noises 50ක් size එක 100යි. So then thereafter these noises will be added to the generator. So you can see, right? So we are getting the generated image from the generator. Then අපි GAN එකෙන් නෙමෙයි, GAN එක ඕනේ train කරන්න විතරයි, right? So we are going to get like images, right? Generated images, let's say generated images like from the generator, right? Generator network, generate network. So it will be taken from the generator and like generator dot predict, right? Generator dot predict. I'm going to input the noise, right? So noise will be input and the generated images will be taken. So then thereafter I'm going to plot it plt dot figure fig size fig size is like, let's say 10 by 10, right? 10 by 10. And yeah, we can, yeah, let's use 10 by 10 for now. And fig size will be 10 by 10, like tuple 10 by 10. And thereafter, for I in range, like we have to check how many images are generated. Generated images shape 0. How many images are generated, we have to check. So it will be 50, right? මොකද අපි noise 50 දාන්න. ඉතින් noises 50ක් දාමුවාම 100 size එකේ noises 50ක් දාපුවාම images 50ක් generate කරනවා. ඊට පස්සේ මොකද කරන්නේ? ඔය 50, so we are going to like go like 50 times, and I'm going to subplot it. Actually, that means in each plot, in a single plot, I'm going to subplot those images. Images 50ම එකම image එකේ තමයි පෙන්නන්නේ, right? I put a figure size එක වැඩි කරමු 20 by 20 වගේ. 50 න ප්‍රශ්නයක්. Then yes, so right, so subplot 50 51, no sorry, I plus 1, nplt.imshow here.imshow generated images I, then cmap array, and yeah, then here some additional parameters I will explain. Final save fig, and GAN generated images network sorry, network. Yeah, actually this should be E, and PNG, right? So that's pretty much everything, I hope. I will explain now what I'm expecting to do here. I will explain it, but let me first run this and check whether any error is there. I will rectify these errors, and then I will explain the whole code. GAN is not defined. Yeah, this should be reshaped at the case. Reshape. Otherwise, like we have 784, 784. Yeah, reshaping node plot, we have to reshape it to 20 by 20. That's the case. DPI equal DPI is basically the resolution of the image. So let me make sure that this is working. Then I will explain everything from very beginning. Actually, this is my mistake. This should be like this should be outside from the inner loop. Right? This should be outside. I mean, I want to plot it at each epoch, not each batch. I want to make sure whether this is so let me take one, get one image, so then I can make sure it's working. So then I will explain. Okay, so meanwhile I'll explain. Okay, so let me reduce the size bit, right? And increase it. Yeah. Okay. So coming from the very beginning, right? So we have like got the MNIST data set, right? So that's it. That's a simple thing. And thereafter that MNIST data set, uh, we have converted the all pixel values between -1 and +1, right? -1 and +1, and we reshaped it like well, we flattened it, right? So we flattened the data set. That's what we did here, right? And thereafter, we developed the generator network, right? So generator network is developed, and The generator network is basically a, you can remember, a decoder kind of a thing, right? Sorry, an encoder kind of a thing, and that's here, right? So we have created a generator network subsidiary, and it is giving a like a noise. I mean, a fake image. So it should be a 784, right? So generator is taking a noise of 100 and 100 and it's creating seven. Sorry, not 100. It's taking a noise of 100 and creating a 784 like a digit, right? So then thereafter, the discriminator is generated separately. So discriminator is basically taking again a image as the input. So you can remember it's taking an image as input. Like it's kind of similar to the output of the generator, and the discriminator is giving like one output, and that output is like a sigmoid neuron which is giving 0 or 1, right? So minus, yeah, 0 or 1, 0 or 1. So that's what we did, and we use a sigmoid activation, right? A sigmoid activation is used, and thereafter, right? So thereafter, what we did, basically we, right? So we got, yeah. Anyway, yeah. Uh, yeah, we are getting the results, but I think issue with the plotting. Anyway, let me fix this and let me explain the others. Yeah, so what I wanted to explain here now, yeah, we have the discriminator and the generator separately, and combining the discriminator and the generator, similar to the method I used implementing the the autoencoder last time. I create the GAN. I combine two neural networks, generator and the discriminator, and this kind of a model is created, right? The GAN. So you can see, as I mentioned earlier, for the GAN. Like this whole thing will be considered as the GAN. So you can see here the input will be the noise. Input will be a noise for the GAN, and also uh, the output will be the sigmoid neuron of the discriminator network, right? Got it. So according to that, I have developed the GAN here. I have developed the GAN here, and so we have the GAN. Now then what I'm going to do, like we are going to train it for 100, sorry, for 400 epochs, right? 400 epochs, this will be trained. And when I print it, like the number, the epoch number, and I'm going to create something called batch. So I hope that you can remember what we implemented in this self-driving car. If you can remember, like, can you remember there was something called batch training, right? Here also the same thing done. The thing is, this requirement is arises. I mean, requirement is arised here due to like uh, we are not going to train the discriminator separately and like at once, right? So we are not going to train the discriminator at once, right? We are going to first train it, right? And then train the generator and train the discriminator, train the generator. Understood? Likewise, we are going to do it step by step, not at once. What's the reason? Now here, can you see that? Okay, so when you are going to uh, important point here. Now, when you are going like using real and fake data, we are going to train the discriminator, right? So that's what we are going to do. Now here, without training the generator, we are going to like add some noise and we are going to get some uh, what noisy images, and those will be considered as the fake to the discriminator, right? So combining those, we are going to train, but like that's not the only thing, right? So thereafter, what we are going to do, thereafter we are going to like uh, freeze the discriminator and train the generator in order to like from the generator, like we are trying to provide real looking handwritten digits, right? So once it done, එකපාරක් එක කළාම, right? එකපාරක් එක කළාම මොකද වෙන්නේ? generator එක improve වෙනවා, right? discriminator එක full වෙනවා. discriminator රැවටෙන්න ගන්නවා. හැබැයි ඊට පස්සේ ආපහු the same thing is done. Why? Like we are getting real 50% real, and now from the train generator we are going to get some fake images. Now in the second time, second epoch, what's going to happen? Now this generator is bit trained one. දැන් කලින් වගේ ඔහේ තිබ්බ random images නෙමෙයි දෙන්නේ. Not like in the second epoch, like it's going to give some better, it's noisy but better than the first one. Now the discriminator is like trained to like identify in between those two. දැන් පොඩ්ඩක් මෙයා improve නේවා දෙන්නේ. ඒවත් discriminator එක තේරුම් ගන්න ඕනේ. Right? ඊට පස්සේ ආපහු what we are going to do? Again, we are going to train the generator. Now the I mean, it's like this, right? So it's like this. Generator is like capable of identifying noisy and real images. So then we are going to like improve the generator bit. Now this should be bit increased again. Why? Like this is started to like generate better images than the earlier case. So this should be again better in order to identify the fake and the real. Then it's again improved, right? So likewise, these are competing to each other, and finally, this will come to this point, right? So that's why step by step we have to do it. So that's why we are going to train it on epochs, and batch training is basically right. Without applying the all images at once, we are creating small batches and do this. So then it will be done like step by step, right? So that's the like we are going to like take 128 images per one batch, and for like every epoch we are going to like we are going to run it for 460 times, right? 460 times, right? Then method, can you remember the batch size is 1 to 8. That means for one batch we are passing 1 to 8 images. එක batch එකට අපි 128ක් images දාලා තමයි train කරන්නේ. So batch count is 1. That means train data shape, that means 60,000 divided by 60,000 divided by 60,000 divided by batch size is 1 to 8. So this is roughly 468. So that means this loop is running for 468, right? So that means what? Like we are getting 1 to 8 random selected for 460 times for single epoch. එක epoch එකකට 468 පාරක් 128 ඒවා 468 පාරක් යනවා. Right? So roughly we are going to, for each epoch we are using 60 images, 60,000 images, but they are selected randomly, right? They are selected randomly. So then right, so they are selected randomly as I mentioned, and yes, yeah. Now we have an issue here. I'm not sure what's the issue. I mean, the perfectly done, but with the plotting, uh, Anyway, yeah, let me. Okay, it's plotting it. I'm not sure. Yeah. I think I figured out the reason. Let me plot 100, then it will be, yeah. Yeah, so anyway, I'll show you the generated images. So that's what you call batch training, as I mentioned last time, right? So like it's going to like first the discriminator, right? Then the generator, discriminator, generator, likewise it's going to step by step train it. ඇයි මම මෙහෙම කියන්නේ දැන් මේ බලන්න හොඳට මේක බලන්න ඕනේ. ඇයි මේ batch training එක වැදගත් වෙන්නේ? මේ epochs by epoch training කරන එක වැදගත් වෙන්නේ ඒක බලන්න. again ඉස්සලාම අපි දැන් මේ අපි හැම වෙලේම discriminator ඉස්සලාම train කරනවා. discriminator train කරද්දි 50% real ගන්නවා 50% fake ගන්නවා. right? හැබැයි මේ fake හදන්නෙත් generator එකෙන්. So generator is going to create this fake, right? At the first time, generator is not even trained. So it's going to generate totally random images like this, right? So then like we can say, okay, discriminator is like very comfortable with identifying fake images. Why? We have like good looking, very real images and like some random noise. Okay? So discriminator very easy to understand the fake one. But what happens then? Like we are going to change the generator, right? We are going to change, we are going to train the generator. So now the generator will be bit improved. Now now like it's like this. Now the generator is coming bit it's bit improved. Now the discriminator should what? Identify what now by what the images generated by the improved generator, right? So then when you are going to train it again, now in the second time, these images, like when you are going to provide noise, these images provided by the generator will be now bit improved. So then the discriminator, like it's going to train, like identify real and fake again. But this time the discriminator is a bit hard, since the generator is trying to like give bit improved images, right? But anyway, let's say, okay, discriminator now really can identify those images again. Then again, the generator will be again trained. Then the generator තවත් improve වෙනවා. දැන් මොකද දැන් නම් පොඩ discriminator පොඩ අමාරු දෙක අඳුර ගන්න. Right? So likewise, we have to like train the discriminator, generator, discriminator, generator. Like that's how we are going to obtain a good generator, right? So batch training is another important thing, right? Without applying the data set at once, we are going to like apply batch by batch, 1 to 8 images, right? So right, so that's what happens. And yes, so here now what we are going to do, we are going to train it, and after every 20 epochs and the first epoch, I'm going to plot I'm going to apply some random noises, 100 noises, and check the images generated by generator. Now you can see after it's been trained, right? So after training it, we need only the generator to get new generated images. So we are like taking the generator and apply noises and getting new images. So that's what we are going to do here. And here you can see after like the first epoch and after every 20 epoch, I'm going to plot it. Now here what's going to do, we are going to randomly generate some noises, 100 noises, and those will be added to the generator, like predicted by the generator, and generator is going to predict generated images. So generator is going to output generated images, right? And so we are going to here subplot. In the same plot, I'm going to plot all the plots. That's what I'm going to do here, right? And you can see these are the randomly generated images after the first epoxy, right? So almost like, right? So how? Let's see, right? So it's like 9. This is like 4. This is like 8. This is like 9. I mean, this is even at the first epoch. මේ පළවෙනි epoch එක තාම. 7 3 දැන් මේ කොහෙවත් නැති images උත් තියෙනවා. දැන් මේවා හැම හොයන්න බෑ. Right? But good, right? Almost good images are there, right? Almost like real looking images are there, right? So you can see that this takes some time for epochs, right? This takes some time for the epochs, but anyway, at 20 epoch, 40 epochs, 400, like so 60, 80, 100, like we can check what happens at each epoch. I mean, like 2020, we are running this for 400 episodes, for 400 epochs. So at all, at each 20 epochs, we can check the output, right? What it gives us, right? Okay, so that's pretty much everything, right? So good, very interesting example, right? But hope you understood. And if you have any issue, please ask. This is a bit complex, not like conventional codes that we discussed. This is a bit complex, like we have like do some advanced things. Now, if you have any confusion or any like unclear point or anything to be clarified, please ask. I can explain it again if you have any missing point here. Yes, you can see now, right? Like very good results are given at like at the first epoch, right? So you will get definitely very improved images you will get after like 20 epochs, 40 epochs, like eventually this will increase, right? Now the other thing is now, like we can't say what noise to monkey one is. I explained this earlier, right? So now I explained this earlier as well, right? So when like random noise, we can't exactly say what noise is should now what noise should be given in order to generate generate 7, generate 2, generate 5. We can't say it like that, right? But anyway, a noise, right? Where a noise is given, there will be some digit generated. So we can't exactly say, okay, in order to create 2, this is the noise should to be given. We can't say it like that, right? So there will be very interesting thing, right? So you can check this, like after training this, right? So let's say like 400 epochs, so it will take some time to train this for 400 epochs. But one thing you can do, you can upload it to the Google Colab and see, and done this quickly. And the other thing is like what you have to do after training this thing, what you have to do simply, you have to save only the generator dot save weights, right? So we need only the generator, right? So what do we mean by this generator? We are going to like save it for a H5 file or a model file. What we mean, like we have a neural network, when like we are going to give 100, like a noise of 100, right? 100 white noise, this is going to give us a 784. And when you are going to like make it 2D, you are going to see a handwritten digit. මේක සේව් කරාට පස්සේ මොකක්ද මේකෙන් කියන්නේ? 100 දිග noise එකක් දුන්නාම handwritten digit එකක් මෙයා generate කරනවා. ඒතකොට ඔයාලට පුළුවන් මොකද්ද? digit එක දාලා බලන්න, sorry noise එක දාලා බලන්න මොකද්ද දෙන digit එක කියලා. ඒ විදිහට ඔයාලට එතන තමයි check කරගන්න තියෙන්නේ. Otherwise we can't exactly say what the noise to be added to get a particular number, a particular digit. Right? Yes, so other than that, anything to be clarified, any issue you are having or any doubt you are having with generative adversarial networks, please? So we have a question. When the generator and the discriminator trained, how they continue with the previous trained best model? Nothing like that will happen, but anyway, the weights and biases are like they will be continuously trained, right? The best model in the sense yes, the thing is now the weights and biases will be continuously trained, so that's how we are going to train. Otherwise, like we can't exactly say. I'm not sure about yes, I'm not sure whether you are asking about the like how we are going to get the best model, or how to like how the neural network identify or how this continues with the earlier trained model, right? But anyway, what's going to happen now, the weights and biases will be continuously trained, and like we can always check the loss, and we can always check the accuracy and get like we can always save the best model as well, right? So we can use the model checkpoints, right? We can use the model checkpoints as well. We have discussed about the model checkpoints, so we can use them as well here, and we can check the best model. What's the best model? I'm not sure whether like it's going to train the accuracy or increase the accuracy and decrease the loss at each epoch, but we can use the model checkpoint and train the best model only. That could be done. Don't we have to reshape the noise to 784 initially? No, the noise is basically, what do you mean? No, we are not going to add you mean this one? This noise? The fake noise, is it? Is this one or this one? First one or second one? Yes, Vasindu? You are talking about this or this? What do you mean by noise? First one, right? No, the thing is now, no need to make it 28 by 28 since the discriminator, can you see the discriminator is expecting, and the discriminator accepts, right? The discriminator accepts right, 784, right? So it also accepts flattened image, right? Yes. Any other issues? Okay then. So I will upload the codes and upload this code and also the video. So please have a look and start working on this. So definitely please try to implement this your own, right? Implement this your own and uh, yeah, you can view the loss actually, right? So you can view the loss. Uh, the thing is now, since we are training on a batch, we can't exactly get the loss here at once, but what we can do, uh, you can like model dot, yeah, after training it, uh, model dot, model dot evaluate, model dot, yeah. So let me check, like since this is, when you are going to like train on batch, this is not viewing the loss, but let me quickly check it and let you know. Mhm. History dot history. Yeah. So you can do it like this. Yeah, you can get the loss model dot. Sorry, you can print it like this. Print the discriminator, right? The discriminator history dot history loss. Right. And also the discriminator also has accuracy. Okay? So that accuracy can be also got like this. And also I hope for the other GAN and also the GAN and also the what you call the generator, you can get it like this as well. Yes, so that's how you are going to get it. So you can add the same thing for the generator and the GAN as well. Right. So any other thing? Okay then, so please have a look on this video and also the code will be uploaded. So please try this your own. And the thing is now we have only passed 5 epochs. So you have run this for 400 epochs and see like what are the now. This is plotting the generated images for every 20 epoch, right? So you can plot this and see how this improves, right? And probably you can run this on Google Colab as well and get fast results. right? Okay, so then I will conclude it from here, right? And we will meet on this Saturday with a very important topic called reinforcement learning, a very fresh and a new topic, and very interesting and a bit complex and bit novel and a bit confusing and interesting topic. So hope you will be there on this Saturday, and see you on this Saturday. And good night, and do your work. And please try to implement these codes and see results, and try to do your work in each week. Right. Thank you very much, and meet you on next time.